Seth wants to know how many positive whole numbers from 1 to 100 are divisible by 2 or 5. He thinks that the answer is 70 because there are 50 multiples of 2. You get that by doing 100 divided by 2, and 20 multiples of 5. You get that by doing 100 divided by 5. Explain why his answer is too large. Well, he is correct in what he said here. However, 10 is a multiple of 2 and a multiple of 5. So Seth has double counted all the multiples of 10. i.e. they will be in both lists. So the answer is actually 60. Because you can take all the multiples of 2, absolutely fine. There's 50 of them. Then you need to take all the multiples of 5 that are not multiples of 2. And those are going to, so we just have to divide it by 2, that 20 by 2, because that gets rid of all the ones that end in 0. We'll just be left with the ones that end in 5. So good start to this question. That's going to help us in part B. In B, we're asked to consider the list of 1,800 fractions and how many are not in simplest form. Explain your reasoning. So, not in simplest form if they share any kind of common factor. A factor greater than 1, in fact, because 1 over 1,800 share a factor, but you can't simplify this because you can't divide by 1 to make it simpler. Well, let's look at the factors, therefore, of 1,800. And I'm going to first of all I'm going to get it into its product of prime factors. There's 18 times 100, which is 3 times 6, or 2 times 2 times 3, times 2 times 5 squared. And I'm going to be left, sorry, I made a mistake there. 2 times, rushed it, 2 times 3 times 3. Let me not rush it. 2 times 3 squared times 2 squared times 5 squared. So it's 2 to the power 3 times 3 squared times 5 squared. You can actually work out the number of factors by adding 1 to each of the powers and then timesing them. 4 times 3 times 3, which gives us 36 factors. The thing is, that's actually not that important. What we want to know is just that they share a factor, and it's actually the prime factors that we need to look at, because all factors will be multiples of 2, 3, or 5. Has to be, because those are the factors of 1,800. Of course, they might be multiples of both. They might be multiples of 2 and 5, like 10, for example. But that's where we're going to link into part A. We might be double counting them. I'm going to talk about two ways to do this question. The way that I did it, which works quite well in this scenario, actually, I think it's a bit quicker than the general method that I'm also going to talk about, which is quite nice, but it's a little bit harder to get your head around. But it's a good one that could work generally. So method one. Okay, so I want to know how many multiples of 2 there are between 1 and 1,800. I can do that by just dividing by 2, because there's every second one. So there's 900. all of these are going to simplify. So like 4 over 1,800, 6 over 1,800, 8 over 1,800, they're all going to simplify because they've got a common factor of 2. Now let's take a look at 3. 1,800 divided by 3 is going to be 600 multiples of 3. But just like we did in part A, we would have double counted, for example, 6. Okay, 6 is a multiple of 3 and we'll go into 1,800, but I've already counted it here. So 300 will be even. And we've already counted these. 6, 12, etc. So 300 will be odd. And we've not counted these yet. That's things like 3, 9, 15. Okay, so I'm going to add that on. Finally, I've got 1,800 divided by 5. I divide by 10 to give 180 and times by 2, 360. But now some of these are going to be even. Actually, half of them are going to be even. So 180 are even. Things like 10, 20. So discard. And 180 be odd. Things like 5, 15, 25. Now we're not actually quite done because now that it might be odd and a multiple of 3. And look, you can see that 15 has already been counted and we've got it here. So we actually need to, a third of the rest will actually be multiples of 3. So like, 35, 45 will be as well. You can see it's every third one that I need to get rid of. And therefore discard 60. And there's therefore going to be 120 new values. 120 new values or factors of 1,800. So the total is going to be that 900 from before. Then I've got that 300 and then 120, which gives me 1,320 values. So quite a lot. And, we could be asked which ones are not going to cancel down, in which case it would be 1,800 minus that 1,320. So remember, this is the 1,320 numbers that share a factor greater than 1 with 1,800. Let me talk about method 2. Okay, so I'm using the answers for this one. So we could construct in a similar sort of way these lists. 1,800 over 2 plus 1,800 over 3 plus 1,800 over 5. And that would be double counting, but it would give you all your multiples. And then we could subtract some of these shared factors. So 1,800 over 6, that would get rid of the common multiples of 2 and 3. Actually, before I do that, just let me work out what each of these is. So this will be 900, 600, and 360. So I'm then subtracting this, which is that 300 from before. That's actually what I did before. But now, it's a slightly different approach. I'm now going to subtract all the common multiples of 2 and 5. So I'm going to divide through by 10. There's going to be 180 of these. Right. And then finally, all the common multiples of 3 and 5. Which is a little bit more awkward. So if I divide by 5, I got 180, and then divide by 3, this is going to be 60. Now, there's just one thing I need to be aware of. When I've added these together, I've actually added the multiples of 30 3 times. Because 2 times 3 times 5 is 30. So I've included the multiples of 30 here, here, and here 3 times. But over here, I've then subtracted the multiples of 30 um, 3 times as well. So at the moment, I am not including any multiples of 30. And therefore, I have to add back on. This is the most subtle bit. And it's why I kind of prefer my first method, because I didn't, I just felt like it's quite intuitive what I was doing. Whereas here, I think it's very easy to miss this bit. I need to add this back on. I've cancelled these out above. So I added up all these multiples. I'm including some double counting, which I then try to subtract by looking at the multiples of 2 and 3, of 2 and 5, and of 3 and 5. The only danger is that you subtract all the multiples of 30, which is 2 times 3 times 5. And so we have to add that back on. So that's going to give 60. Okay, and if you add these up, and why not, I'll have it a go. I'm going to get 1,500, 1,860. Then I'm going to add these up. 240. It's going to be 540. And I just have to add 60 back on. That's going to be the same as doing 1,860 minus 480. Maybe that wasn't the best way to do it, which is going to give me 138. Is that right? 80 again. And that's, oh, sorry, I think I've made a mistake somewhere. So I've just found it. That should have been 120. My bad. Which means I was actually subtracting 600, which it just actually makes sense to change this to 1,260 plus 60, which gives us the 1,320 as before. So this is a solid method and could more easily be extended to if you had more factors, and it's actually called the inclusion-exclusion principle. So, you might want to investigate what would it be if you had 4 numbers? You're always going to kind of get this for 3 numbers, it's always going to be this sort of thing. Just cancel out these here. What about for 4? So apologies about the small mistake here. Hopefully you spotted it as I was doing it and were like, what's happened here? Um, but yeah, I'm happy with that explanation and my first method as well. So that is the answer to this question. Well done.